All right, today we're diving into the architecture of matrix operations, but I want you to think about this a little differently. We're not just looking at boring grids of numbers. We are stepping into a parallel universe, one that has its own unique and sometimes weird laws of physics.
So, if we really want to understand this world, we have to get a handle on its rules. How do these building blocks actually interact? How do they combine and transform? Let's explore the fundamental laws that govern this whole strange and powerful architecture.
We're going to start with the simplest laws of interaction in our matrix universe, how they scale up, how they merge together, and how they invert their values. These are the absolute fundamentals.
Okay, so imagine a single lone number, what we call a scalar. Think of it like a universal force. When it interacts with a matrix, it doesn't just nudge one little part. Oh no, it sends a pulse of its value to every single component inside that matrix all at the same time.
And we call this a distributive pulse. See how the scalar 2 just hits every single number in the grid? It just spreads right through it. And here's the really important part. The order doesn't matter one bit. Multiplying the matrix by 2 gives you the exact same result as multiplying 2 by the matrix. That property has a name. It's called being commutative.
But, this universe has some pretty strict boundaries. And here's a hard and fast rule. You can divide a matrix by a scalar, no problem. But you can never divide a scalar by a matrix. It just doesn't work. The operation is literally undefined.
And this is exactly why that rule exists. See, division is really just multiplication in a clever disguise. Dividing this whole matrix by 2 is identical to multiplying it by 1/2. It's really just a change in perspective, not a totally new operation.
So let's move on and see what happens when two matrices interact directly with each other. The very first rule of merging them, or what we call addition, is that they have to be the exact same shape and size. Think of it like a structural compatibility check. If they don't match, they can't combine.
So the crucial point here is this simple element-by-element merging. The top left element adds to the top left. The bottom right to the bottom right. You get the idea. It's a super straightforward combination that, just like the addition you're used to, is commutative. A plus B is the exact same as B plus A.
And subtraction? Well, it turns out it isn't really a brand new operation. It's actually a two-step process. First, you take that second matrix and you flip the sign of every single element inside it. Then you just add them together like we just saw. But because of this process, all of a sudden, order matters. A minus B is definitely not the same as B minus A.
Okay, so we've covered the basics. Now we get to it. We've arrived at the most complex, the most fascinating, and honestly, the most counterintuitive law in the entire matrix universe: multiplication.
So, what is the deal with matrix multiplication? I'll tell you this, if you think it's just multiplying the numbers in the same spots, you are in for a serious surprise. It is a completely different kind of interaction with its own very unique machinery.
This is the first, and I mean the absolute most important rule, the lock and key mechanism. To multiply two matrices, the number of columns in the first one must match the number of rows in the second one. If they don't, the whole machine just jams. The operation is a no-go.
But once those dimensions are compatible, the dance begins. To get each new element in the final matrix, you take a row from the first one and a column from the second. You multiply their matching elements, and then you sum up the results. And this little dance gets repeated for every single row and column combination.
And this right here shows the biggest, most mind-bending deviation from the math we all know. Multiplying matrix A by matrix C, it works perfectly because the inner dimensions match up. But try to flip them. Try to multiply C by A, and the inner dimensions no longer match. The operation completely fails. This is the ultimate proof that matrix multiplication is not commutative.
Okay, let's just pause and catch our breath. Let's consolidate everything on this diagnostic table. So scalar multiplication is pretty flexible. Addition and subtraction, they need identical sizes, no exceptions. And multiplication, well, it needs those inner dimensions to match up perfectly. And notice how only scalar multiplication and matrix addition are actually commutative. That's a huge takeaway.
So now that we understand the laws of interaction, the physics of this universe, let's meet some of the special primal elements that exist here. These are matrices with really unique properties that play a foundational role in everything.
First step is the transpose. Now, this isn't an operation between two matrices, but a transformation of just one. It totally reorients the structure by, get this, flipping it along its main diagonal.
It turns every row into a column and every column into a row. Kind of cool, right? Next up, we have the anchor of nothingness. The zero matrix is pretty much exactly what it sounds like. It's the structural equivalent of the number 0. If you add it to any matrix, absolutely nothing changes. And if you multiply any matrix by it, well, everything just collapses into another zero matrix. So if the zero matrix is, well, 0, then this is the matrix version of the number 1. Meet the identity matrix, also known as the anchor of stability. It's always a square matrix, and it's got this signature look. 1s running down the main diagonal and 0s literally everywhere else.
And its power is exactly what its nickname suggests: stability. It's what we call an invariant transformer. When you multiply any matrix by a compatible identity matrix, it leaves the original matrix completely, totally unchanged. It's a cornerstone of all of matrix algebra. So we have the laws of physics, and we have the primal elements. Now let's see how a master architect can put this entire toolkit to use to build and solve really complex expressions within this whole matrix ecosystem.
And here it is. This is the payoff. With all these rules we've learned, we can now confidently navigate a complex expression like this one. We know to do the scalar multiplications first, then the addition, and finally the subtraction, making sure all those dimensional rules are followed every step of the way. It brings a real sense of order to the chaos.
This, right here, this is the big aha moment. The matrix universe isn't completely alien to us. It actually has clear parallels to our world of real numbers, with its own versions of 0 and 1. But that crucial difference, that one massive point of divergence, is that A times B does not equal B times A. Non-commutativity is its absolute defining feature. We've just mapped out the basic arithmetic of this structured reality. It shares some vocabulary with our numbers for sure, but it operates on a much more rigid, multidimensional syntax. And that leaves us with a really fascinating final question. If this is just their arithmetic, what else is possible in the matrix universe?